Hey again, guys. We're back again, moving forward to talk about this thing called the unit circle. In the last lesson, we refreshed our mind on what we learned in geometry about right triangle trigonometry, like sine, cosine, tangent, all of those trig ratios. We're going to move forward now and start to apply trig functions into this thing called the unit circle that'll give us an algebraic representation of those trig functions. But we got to understand some basics about this thing called the unit circle first. It's going to be an extremely important topic as we move above and beyond Algebra 2. So first thing, we want to talk about number 1. It says the x-coordinate of a point on the graph is 3/5. We want to know, what does this tell you about where the point might lie on the unit circle? And we'll find any possible y-coordinates of the point and plot them on the unit circle. I encourage you to pause the video and think about this on your own, and then you'll be able to compare your answer to what I come up with here. All right, hopefully you paused the video and thought about this on your own. One thing we can think of here is this circle. This point out here, since it's a unit circle, we'll say that this is just 1 unit out. We weren't really given any specification. If we thought this was 1, that's okay, but let's just call the radius of this circle all the way out 1 unit. That's going to be helpful because we can break every tick mark into fractions. Like this would be 1/10, because we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way out. So this mark right here would be 1/10, would have 2/10, 3/10, 4/10, 5/10, 6/10, and so on. But we want to know where an x-coordinate of 3/5 is. Well, remember, 3/5, if we want that to be an equivalent fraction with a denominator of 10, because that's what we're working with, well, we'd multiply 5 by 2 to get 10, which means we'd have to do the same thing to the top, basically doubling 3/5 to an equivalent fraction, and we get 6/10. So 3/5 should be at 6/10. Here's 1, 2, 3, 4, 5, 6. This is 6/10, or really 3/5. So what we can do now is to find the y-coordinate, we can draw a vertical line. So I'll draw a dashed vertical line up and find a point on the circle. So we have this 1 point up here, but what if I went the other direction? Instead of going up, made a dashed line down. We have another point down there. So now we have this point. We know this is 3/5, and we want to know what that y value is. Well, same thing, this is 1 unit up, because everything is perfect on a circle. If it was 1 to the right, it's also 1 up, which means each of these is 1/10 again. So to get up to this mark, we would count 1, 2, 3, 4, 5, 6, 7, 8. That's 8/10, which, if you simplify, is actually 4/5. So we could write this as 4/5. And if we just thought real quick, well, we know the x value of this point is 3/5. What's the y value? It's just the same thing in the opposite direction. So pause for a second and think, what would the y-coordinate be on this point? Okay, so it was 4/5 up here. Hopefully you should have thought that this is -4/5. It's just in the opposite direction. We have this symmetry involved in circles. Everything kind of reflects. So any possible y-coordinates of the point would be 3/5, comma 4/5, or 3/5, comma -4/5. All right, similar idea. For number 2, they tell us the y-coordinate. So they're giving us a y-coordinate this time. Is a point on the unit circle at negative 0.4, or really this is 4/10. Negative 4/10. So if you were to write negative 0.4, negative 4/10 as a fraction, that's negative 4/10, which you could simplify to negative 2/5 if you really wanted. So let's think, where is that on this circle? Negative 4/10. Well, here is negative 1/10, negative 2/10, negative 3/10. There's negative 4/10. I'm sorry, actually I went the wrong way. They gave us the y-coordinate of negative 4/10. Going a little too fast. Actually be negative 4/10, so 1, 2, 3/10. Here's negative 4/10. I'm sorry, hopefully I didn't confuse you there. So now we want to figure out what the x-coordinate is. Well, here's the point that corresponds with that. There's 1 right here. But if we went in the other direction, there's another point right here. So now we've got to figure out that x-coordinate. Well, let's draw a dashed line up. Estimating, that seems like it's a little more than, well, this is 9/10 right here. So a little more than 9/10. Same idea here, a little more than negative 9/10. We got to figure out what that actually is. So one of the most helpful shapes we have is actually a right triangle. So let's actually draw that. Let's form a right triangle with this point. So we'll draw a line out to here. Already have this vertical line. There's a right triangle. And we can do the same thing the other direction. What's really cool right now is we know that the radius of this circle is 1. So that means even this is 1. Even this is 1. It's the power of the unit circle. The radius is always 1. And we know this side of the triangle. This is 4/10. Yeah, it's negative, but because it's a length, we'll just not worry about the direction right now. It's just 4/10 down. Now we just got to figure out the remaining side of the triangle. What is this horizontal x distance both ways? You only have to do this once because it's really the same triangle, just symmetrical, flipped over the y-axis. Well, if we know two sides of a right triangle, we want to figure out this x length. What could we use? Think about it for a second and maybe give it a shot. Okay, well, we can use the Pythagorean theorem. Pythagorean theorem tells us that, in this case, x squared plus the other side, 0.4 4/10 squared, should equal the hypotenuse squared. X squared plus, well, 0.4 4/10 squared, if you use a calculator, or just think about it, would be 0.16. 4 times 4 is 16. 16 hundredths equals 1. Subtract 0.16 from both sides. We have x squared equals 1 minus 16 hundredths. Do that subtraction. 1 minus 16 hundredths would give us 84 hundredths. Take the square root of both sides, and x would equal 0.84 square rooted. If we approximated that, you could get a decimal value, but I'm going to leave it like this because that's an exact answer. So here is our x-coordinate. This length is negative 0.84 because it goes left. And this would be the opposite, positive 0.84. Sorry, and they're square rooted. And the square root would be So we have our points 0.4 comma square root 0.84. I'm sorry, I wrote that backwards. X comma y. Negative square root 0.84 comma 0.4. That's negative because it went down. This is positive square root 0.84 comma negative 0.4. And those are our 2 points. So hopefully that gives us an understanding of the symmetric nature of a unit circle. We have an idea that the radius is always 1 and we can always work with that. The Pythagorean theorem and building right triangles can get us different distances as long as we know at least one of them. Alright, so task 2, it says all points are 1 unit from the origin. So we know that now from the unit circle. All points are 1 unit from the origin. That's super important. We want to choose one of the points and be prepared to describe its location using only words. So choose one, pause the video, and write your own statement describing where it is. I'll do the same. So my description will be point P is the point in the 3rd quadrant, or in quadrant 3, closest to the y-axis. So that's how I'm describing my point. Compare that to how you described your point and think about maybe what similarities and differences you have. Then pause the video and decide, actually, if I'm specifying this point, go ahead and circle on the unit circle here where you think the point I'm describing is. Okay, hopefully you paused it. Here's the circle. I'm describing something in quadrant 3, so it has to be over here. And then I mentioned that it's closest to the y-axis. So this would have to be the point I'm talking about. You can describe any points in that nature, but one really handy way to do it. Say I draw a radius out to that point. What happens is we have this angle of rotation. We're always going to start here on the positive x-axis. There's an angle of rotation that takes it all the way from there to that point's radius. This angle we're going to call theta. Theta is a Greek letter, probably worked with it in geometry. T-H-E-T-A, theta. So that angle right there describes the point P. So we could say this point is a point P, I'll call it P, at angle theta. That'd be a really efficient way to describe this, and this is true because there's only one point that can be at that angle. No other point on this circle could have this same angle measure. This is the only point that would have that, which is pretty cool. So it's really simple, and that's especially because every point is 1 unit away. Only one angle will describe that point. So all we have to do is specify what angle we're at. So this unit circle, it's going to be heavily involved with the angle of rotation starting at the positive x-axis all the way to the radius that that point is at. All right, task 3. It's about measuring circles. So let's look at the radius of a circular object and think about how many radii is plural for radius, how many radii does it take to go halfway around the circle? So what the heck do I mean by that? Well, for a second, let's just draw a circle. I'm going to do it in purple. Or that came out red, that's fine. Yeah, I'll make it purple. Alright, so a radius is, again, the distance from the center of a circle all the way to the outside of it. So distance from the center to the circumference. So that's one radius. We'll actually use that as a unit of measure right now. So this is one radius. So pretend this is like a unit of measure is what I'm saying, like a foot is a unit of measure. Let's consider this to be like its own unit right now. In fact, we'll just call it r for the moment. If I were to take this radius and bend it, how many of them could I fit around, what's it asking? Halfway around the circle. So if I were to take this, come up with an estimation. I encourage you to just pause the video and think, maybe how many of these? Maybe draw a rough sketch and think, how many approximately could you fit? Thought is, I'm taking this radius and I'm putting it around the circle somehow. And then I'm bending it so that it fits along the circle. Something like that. How many more would I have to do to fit halfway around? Right, this is going to be hard to get exact because I feel like I changed the size and it's hard to draw that exact same thing. If you really want, you can get a circular plate, cut out a string, that's the exact radius, and try to see how many times you can fit that around the circle. In fact, that's what we would have done if we were in the classroom right now. But what's cool is I actually have an application that I can do this with. So notice this blue line right here, that's the radius of this circle. What I'm going to do is I'm going to change the angle. Notice the black line is changing the angle of it. Well, now I have one radius. It's basically what I just drew on the document. Well, there's another radius that came up. Now it's moving out, bending, and we have two of them. I want to see how many fit halfway around. Now I have three of them, but I haven't quite gone halfway around yet. So we'll go a little more, and there I am, halfway around. So we have 1, 2, 3 full radii, and then just a little bit extra down here, a little portion of that yellow. So it seems like we have a little bit more than 3 radii. So that's my answer. I'll say, about how many radii does it take? 3 full radii. Plus a little extra. So it's like a fractional amount of 3. So maybe like 3.1, 3.2, I don't know, just a little bit extra. So if I were to continue drawing this, it's like would have another radius right here. This is R. This was 1R. We had a third radius, and then there would be a little bit more attached on the end to go halfway around. Right, about how many radii does it take to go all the way around the circle? So again, I can continue drawing that, or let's go back to that app. If I kept going, I want to go all the way around the circle. and then count them up. I have 1, 2, 3, 4, 5, 6 and change, which makes sense. We're basically just doubling that 3 and change. So now it's 6 and a little extra. So 6 full radii plus a little extra. So my guess, like 6.2, or maybe double this, 6.4, somewhere in between there. You got to figure that out though, probably. And that's the next part. What is the exact number of radii that fit around the circumference of the circle? And explain how we know. I encourage you to pause the video and think about that. Try to remember what would tell us the distance around a circle, the circumference. Do we have a formula that tells us that? Think about what the radius is. Try to calculate that. All right, refreshing ourselves. You probably remember from earlier math classes that the circumference is equal to pi times the diameter. So it's the diameter multiplied by pi, which is just this constant of proportionality. Which we know is equal to 3.14. And this is the diameter. Well, we can also write that in terms of radius. We know that the diameter is all the way across the circle, which is just 2 radii. So I could also just say that the circumference is equal to that constant of proportionality pi times 2 radii, because that's equal to 1 diameter. Multiplication is commutative, so the order doesn't matter. So we could arrange that as 2 pi r. And we can use this formula to think about what we were talking about. Well, in our case right now, the radius is 1 radius. We were calling the radius a unit of measure. So 2 pi times 1 radius. 2 pi times 1 is just 2 pi. So the distance around the circle is 2 pi radii. This is really important. Distance around a unit circle, because the radius is 1, is 2 pi radii. We'll come up with a new word for this right now in a second. So what is the exact number of radii that fit around the circumference of a circle? 2 pi. Well, what is 2 pi? Approximately, that's 3.14 times 2, so 6.28 radii. Oops, 1D. All right, and lastly, why doesn't the number of radii that fit around the circumference of a circle depend on the radius of the circle? Well, if we think about this, the radius of a circle really depends on what we're scaling it by. So if I were to make this radius bigger than just a value of 1, like if we're 2, everything would be scaled up. The circumference would also be scaled up. So changing the radius just scales the entire circle. So I already wrote this. I'll just paste it in here. And this is because all circles are similar to each other. Do that again. So because all circles are similar, if we scale the radius to a different size, like I said, 2, then the circumference will be scaled by that same factor. So the circumference will also get larger. Dang it, I did that again. And this is where we come up with a phrase for the distance around the circle. We start to call this, instead of 2 pi radii, we'll call it 2 pi radians. Angle of rotation around a circle is 2 pi radians. So like we went 2 pi radians all the way around this circle. 2 pi radii was the distance all the way around. Well, this angle of rotation inside, theta, is equal to 2 pi radians. Alright, so let's look at a little example here with a bike wheel. Let's say this bike wheel has a 1 foot radius. So we're actually giving a real unit of measure, 1 foot. The wheel rolls to the left, so it starts to go counterclockwise. This is counterclockwise CCW. First of all, what is the circumference of the wheel? I encourage you to pause the video and try to answer that question. Alright, so circumference, well, we have a formula for it now. We pretty much just answered this question. The circumference would be equal to 2 times pi times the radius. Well, what's the radius? It's 1 foot. So it would be circumference is equal to 2 times pi times this 1 foot radius. Well, 2 pi times 1 is 2 pi. It will be 2 pi feet. Well, 2 times pi, this will be approximately 6.28 feet. So the circumference of this wheel is 6.28 feet. Alright, so what I want you to do is try to mark this point, a new point. This is point P. Mark a point Q on the unit circle, or on this wheel I mean, where P will be after it's rolled 1 foot to the left. Be prepared to explain your reasoning of that. Alright, so if I were to mark this, I know that it has to go 1 foot. Basically, it's just going to travel this radius again. So this radius again, if I were to like pretend I scaled it up and bent it, it would probably hit somewhere right around here, Q. And my thought on that is, since the radius is 1 foot, the point P, it'll have rotated 1 radian to get to Q. So, I've already answered this. Or maybe not. So since the radius is 1 foot, the point P will have rotated 1 radian to get to Q. So basically what I'm saying is we have this point Q up here. This point P, it'll have rotated 1 radian to get to Q. because of that 1 foot radius. Which is pretty cool because now we know it just depends on what the radius is, hence the word 1 radian of rotation. This angle depends on the radius. Alright, same idea. Mark the point R where P will be after the wheel has rolled, this time 3 feet to the left. And what angle in radians does P rotate through to get to R? And explain your answer. Right. Same idea for me. This time though, instead of just going 1 foot of rotation, it did that. It went 3 feet. So I'd have another 1 foot and another 1 foot, which means just like in that demo I showed you, it would probably be about here. This will be the point R. Not quite halfway around because it was only 3 feet. So R will be approximately there. Do this in blue. Alright, and if I think about what this angle of rotation is, well, it went 3 feet, so this should be 3 radians. And my explanation, this time the wheel will have rotated a distance of 3 times the radius. So P will have rotated an angle of 3 radians to get to R. So it went 3 feet, meaning the angle of rotation was 3 radians. Alright, number 4, this time where will point B at, or point P be after the bike has traveled pi feet to the left? 10 feet, or 10 pi feet and 100 pi feet. Encourage you to pause the video and try to mark those points too. Alright, this time, pi feet, well in the previous example, we talked and we decided that halfway around was about 3 full radii plus a little extra. Well, that seems like it's coming to approximately pi, 3.14. So that little extra change that we had, that was about 0.14. So this would be our new point. This is, we're wanting to call it, we didn't really give it a letter, I guess, so I'll call it T. And the angle of rotation all the way through to here would have been pi radians. And my explanation is that pi feet is half the circumference. If I were to calculate that, the circumference is equal to 2 pi times the radius, which was just 1. Well, half of 2 pi, half the circumference, is 2 pi times, whereas 1/2 times 2 pi, doesn't really matter the order. So half the circumference is equal to pi. So pi feet is half the circumference, so it will be directly opposite P. What about 10 pi? Well, all the way around once, do this in orange. If I were to go all the way around once, no, that was a 2 pi foot rotation all the way around. So this angle is 2 pi radians. But what would happen if I went 10 pi? Well, one time around is 2 pi. Go down here and write this. Let's think, what is 10 pi? Well, it equals how many 2 pi's? I'd have to add 2 pi 5 times, or really just 5 times 2 pi. That would equal 10 pi. So basically that would just be 5 full revolutions. So basically that should take us back to the same spot P was at. We'd go 2 pi once, 2 pi again, so that's 4 pi, 6 pi, 8 pi, 10 pi would be back at point P. So 10 pi feet would rotate P back to where it started. But after 5 revolutions. So the wheel would revolve 5 times. What about 100 pi feet? Think about that for a second. Right, well, same idea, 100 pi. What does that equal? Well, if I tried to write this in 2 pi, what would I have to multiply it by to get back to 100 pi? Well, 50 times 2 is 100, so this time it would be 50 revolutions. So 100 pi feet would rotate P back to where it started after 50 revolutions. So we can keep going around and around and around the unit circle. So 10 pi radians would just bring you back to where you started. 100 pi radians would bring you back to where it started. Alright, and after traveling some distance to the left, the point P is at its lowest location in its rotation. How far might the bike have traveled? Well, let's draw another circle for this. Know that point P starts right here, but it's going to be at its lowest point in its rotation. So this means it's going to be at the very bottom of the wheel, so right here. How far might it have rotated? What we do know is that all the way around, back to here, that would be 2 pi feet. If it went all the way around in one full rotation. We know that halfway around, that would have been pi feet. If it rotated halfway around. Well, this was 1/2 of a rotation. This was one full rotation. Well, this would be 1/4 of a rotation up at the top, which means this would be 3/4 of a rotation. So what we can do is we can take one full rotation, 2 pi. What do you think you could do to it? Well, we can multiply it by 3/4. Since it rotates 3/4 of one revolution. Or what if it actually kept going? Could go just 3/4 of a revolution, but what if the bike rotated all the way around, kept going, and rotated again to here? Well, it would have already went 2 pi. Well, another rotation, 2 rotations, would be 4 pi. So we could say, or 3/4 times 4 pi feet. Or what if it went all the way around again? That would be another 2 pi. So we could say, or 3/4 times 6 pi feet. Think of what would come next. Probably 8 pi, then 10 pi. So really any multiple of 2 pi feet. Or 3/4 times any multiple of 2 pi feet. Alright, so that wraps up everything. If you're unsure of anything I said up there, please read this summary. This explains in depth everything, summarizes it all, annotate it like we would in class, and hopefully this will explain a little bit more to you. You'll have an assignment with this as well. Please contact me for office hours or tutoring should you need it. Hope you guys have a good week. Seniors, this is your last week. Congratulations. And this is your last assignment. You're welcome. All right, guys, have a good one.